It's my honor to welcome each and every one of you to the third Passive House Happy Hour of 2021 and the 44th session hosted by our wonderful Passive House Accelerator. Thanks for joining us. We welcome everyone from all Passive House communities, as well as everyone else working to create zero emissions buildings with less embodied carbon. Turn on your cameras if they're not on, because we want to see your face, and turn on your microphones because we want to hear your voice. And let's raise a glass this evening to the U.S. rejoining the Paris Climate Accords.
Cheers.
All right. Cheers. And to the shattering of barriers, whether they be gender, racial, or plain old resistance to change, because we are the change and we are here now.
Amen.
Ooh.
Yes, we're here.
Cheers.
All right. So go ahead and please mute your mics now and grab your favorite beverage, more of it if you just drank a couple of good gulps, and settle in because we've got another great show for you tonight. First, we've got a great video that I'm going to let Zach introduce, and then we have a presentation from our friend and repeat guest, Lois Arena of Stephen Winters Associates, who's going to let us in on some new lessons learned regarding VRF systems. And with that, over to you, Zach.
All right, fantastic. So, Tom, are you here? Tom Bassett-Dilley. I'm going to show off a video that Tom just published.
I'm happy to be here.
All right, thanks for being here, and thanks for sharing the video. So, I'm excited about showing this video for a couple of reasons. One is that one of the main reasons that this community is so fantastic is that we're a community of folks who are sharing best practices to get to a low carbon future. And today is one of those days where I think all of us are feeling more hopeful than we were maybe a couple of weeks ago about that future. And so I think that this is a great kind of example of the kind of information sharing that we do as a community. And I want to celebrate Tom for sharing that with all of us. And another reason is that it's a great primer on Passive House, because this is an introduction to Passive House and the digital tools that are available, particularly in the case of this video through FIAS tools, but we also know that there are PHI tools. I say that in the spirit of unity, which was a big theme today in Biden's speech. And so if you're new to Passive House, this is also a great primer on what Passive House is about and the power that it gives architects and designers and builders to realize the future that we all want to see. So here we go.
Can I say one thing, Zach, before you roll it?
Please do.
So this was requested by the AIA 2030 group because my firm was one of, I think, 47 this year that made the 2030 targets. And so for those of you who are architects, AIA members, or just want to join, there are going to be a series of kind of webinars, one focused on small firms like mine, one medium firms, and one large firms, just kind of how did we get there? What did we do to do it? And so what do you want to share in 4 or 5 minutes that can help other architects along? So that's the audience that this is made for.
Great, thank you. So here we go.
This is our decade to clean up emissions. How do we as architects ensure that the buildings we design and remodel today assist and not hinder the making of a clean energy world? My answer is that building design must be energy design. We need to be as expert in building energy as we are in other areas of design and not let it be an afterthought. And the good news is that we have the digital tools to do that as an integrated part of the design process. I'm Tom Bassett-Dilley, architect and certified Passive House consultant. In 2006, I formed TBDA to pursue sustainability, and I knew that energy efficiency would be central to the work. When the crash of 2009 slowed things down, I went to the Passive House Institute US, FIAS, to take certified Passive House consultant training, and it was the best move I could have made. I left with the building science knowledge and energy modeling tools to thoroughly understand the energy impacts of design decisions in the design process. Knowledge is power. Let me give you a couple examples. This is a source zero passive house, source zero being FIAS's term for net zero, that the owners named Acorn Glade, certified last year after the solar PV went on. The aim here, as with all our work, was to marry performance and aesthetics, which means integrating the energy model from early schematic design. The idea was to create a compact, tough exoskeleton that peels back like an acorn where people and sunlight enter, and to use sunlight to organize spaces inside. The focal space of this house is the stair hall, with massive windows across from a wall of site-salvaged walnut. Once we have a massing concept in design, we make a simple SketchUp model of the thermal envelope and import it into Woofy Passive, the energy modeling program for FIAS certification. We use Woofy Passive for non-passive house projects as well. It's our go-to since it's detailed, comprehensive, and verified. There's a lot of input to get the model up and running: assembly R values, mechanical system performance, ventilation schedules, and the like. But given our experience, we can usually get a first pass in just a few hours. And that's when the fun begins. We have a lot of knobs to turn, so to speak, to see what different orientations, shading, windows, R values, air tightness levels, and appliance efficiencies have, not just on the overall energy, but also on the heating and cooling annual demand and peak loads. I think of it as a tool that we use to tune the building to its environment and to test the economics of solutions. The model also gives us an annual energy target to use in sizing the PV array. Mind you, modeling and usage can vary widely, but this gives us a starting point. We use NREL's PV Watts program to get an approximation of the PV array size, and then work with the PV installer to fine-tune that based on their product lines and more accurate solar modeling. New buildings are relatively straightforward, we find, but retrofits, arguably the bigger, more urgent need, tend to be more complex. We find the energy model helps us and our clients visualize the value of retrofit components. This example is for a classic Chicago 2 flat. We use the model to show overall energy reduction, furnace size requirement, annual energy costs along the way. With this knowledge, we can design the passive retrofit so that a PV array that fits on the roof can get us to our target EUI. The energy reduction demonstrated here is widely achievable in our Climate Zone 5 older buildings. They tend to waste most of the energy that comes their way due to low insulation and air tightness levels. We must massively scale up the pace of deep energy retrofits if we're going to decarbonize, and this kind of modeling is a tool to guide good decisions as we build a library of case studies. As the pace of cleaning up emissions accelerates, architects who can confidently guide retrofit and new construction solutions toward low and zero carbon will be the more relevant and in-demand practitioners, I believe. I urge all small firm leaders to invest in the training, to make energy model part of your process, and to help lead climate progress in the construction sector. Thank you, and carry on the good work.
Thank you, Tom. That's great. Appreciate it.
Thank you. My pleasure.
And thanks for joining us tonight. I know you have a lot. You've got a big meeting going on as well, so we appreciate you being here. All right, so great. So we are going to jump into small breakout rooms now, and we have 5 minutes to introduce one another. So that goes by quickly. So make sure that you try to get around your whole group in this 5 minutes. Let me create the rooms, and you may have some celebratory comments, and that would be great. We can share those with one another. See you soon. All right, I'm gonna.
So Harvey, did you say the white boots? Because I didn't hear the white boots.
I didn't hear anything about footwear, but I'm gonna move on because we have a great program. I don't want to, and I have a couple things to say before we get there. So every week we have the Passive House Week in Preview article that we publish on the Passive House Accelerator that is information about what's coming up in the current week. We just had this great Construction Tech Tuesday yesterday. What? Can everyone see this? I get paranoid.
Yes.
Okay, good. All right, good. Construction Tech Tuesday was awesome yesterday with Eco Achievers. talking about third-party verification. Tonight, of course, we have Lois Arena. The Passive House podcast features Brett Seriani of Seriani Designs from Australia. A great conversation with Matthew Cutler Welsh about architecture and structural engineering and the impact of structural engineering on operational carbon emissions as well as embodied carbon emissions. Really great conversation. Please check that out. We've got our list of building science and Passive House gatherings, including our own Susan Rowley talking about the fact that bike racks will save the world again, which will be really interested to see the case that she makes around that. With Building Science Fridays with Mark Willey. Should be a great show, and all sorts of educational opportunities, of course, from FIAS and NAPHN and Building Energy Exchange and PHI and AI New York. I'll talk a little bit more about this one at the end of the program. So please check all those links out. And also, I know that Deb, you had there's a job announcement for an RMI position. So Deb, please, I know you shared that in chat at the beginning of the show, but please share it now so that people can see this cool opportunity that's happening at Rocky Mountain Institute. And with that, I'm going to hand it off to Prudence.
All right, thanks, Zach. So I'm excited to introduce you all again to Lois Arena. If you haven't met her before, she's phenomenal. She's the Director of Passive House Services at Stephen Winters Associates. And Lois actually got her formal start in sustainability during her undergrad, could be earlier, she can tell us, but she got a bachelor's in forest and wildlife management. Yay for the critters and the trees, Lois. That's awesome. And then after that, she went on to get her master's in civil, environmental, and architectural engineering and building systems. She's got a lot of experience, like over 25 years of experience in the building science field, and both in new and existing buildings. And, you know, as a leader in our community, she works on some of the largest and most tricky and difficult passive house projects. She's also co-authored and presented training programs about energy efficient building practices to professionals all across the architecture and engineering world. Lois, thank you so much for joining us again, and we're excited to hear what you have to share with us about VRFs.
Thanks, Prudence. Okay, I'm going to share my screen. You guys give me the the thumbs up if you can see it, and if we're in presentation mode.
We
not
can
in
see
presentation mode.
Not yet, not presentation yet.
Now?
Yes.
Yes.
No.
Okay. Okay. All right. So for those of you who don't know me, hello. Thank you very much for inviting me and for attending. We're going to be talking about VRF, which are basically the large scale building versions of heat pumps. Okay. So we're going to, you know about our firm. We're a consulting firm. My group is Passive House. We do large scale Passive House. Prudence just told you. So what we're going to go through today is very, very quickly, in 15 minutes, we're going to talk just some basic definitions of VRF, not all heat pumps and everything. I'm assuming you understand how a heat pump works. Major system components, the pros and cons of these systems, design considerations for comfort, operations considerations, what we're seeing in the field right now, what we still don't know, and what we're going to be doing moving forward. And I just want to do a preemptive strike. If anybody here is from a VRF company, this is not a downer on VRF. This is just lessons learned and sort of here's a heads up if you're using these systems. And I want to tell you, if you're using them in your first year, just take a deep breath. You have to commission your building for the first year, like any other building system, but it's just more eye-opening in Passive House, right? It's like just at the forefront. Oh my God, why is it not working like it's supposed to work? So variable refrigerant flow is what VRF stands for. They're generally modular. They're outdoor units, approximately 6 to 12 ton size. That's the scale we're talking about. And one outdoor unit can be attached to many indoor units of many types. And you have the expansion valve, which does the extraction or input of the heat into the space in the indoor unit, the terminal unit, what we call. And you can have floor mounted, you can have concealed ducted units with short duct runs, you can have just a ceiling mounted unit, and you can have a wall mounted unit. There's all kinds of options for these, and they all have their pros and cons. our focus today is just on how these things operate and my general recommendations from what I've seen so far. And if you are in the industry, or if you have more experience than I do in this, please shout it out at the end. So air source, heat pumps. Heat pumps, I just want to make this clear, are not a renewable energy technology. Geothermal is not a renewable technology. It is a system that takes heat from one place and transfers it to another place, okay? So an air source heat pump, like the VRFs that we're talking about for these large scale projects, take heat from the outdoor air and move it to the indoor air, or they push heat to the outdoor air after they take it from the indoor air, right? A heat pump can move it in both directions. So I just want you to understand that. You're going to hear the terms water source in other areas where a heat pump takes heat and transfers it to from a water source and moves it around the building. Ground source takes it from the ground and moves it to the rest of the building. And then there's inverter driven, which is a variable speed compressor. We're talking about variable refrigerant flow technology right now. So the main considerations when you're looking at these systems are, do they have the capacity that you need? Can they supply the heating you need in really cold climates, right? So we have what's called cold climate heat pumps, cold climate VRF systems. You want to make sure you're looking for that in cold climates. Capacity, actually how small can we go? Because we all know our passive house projects are, super low heating loads. What's the smallest units we can get for the terminal units inside the project? And then can we get enough out of that same unit for cooling, right? So in our projects that we see in the Northeast of the United States, we're seeing like let's say 1 ton of heating would equate to probably 4 tons of cooling, because our projects are cooling dominated. So that's the kind of ratio you're looking at. It can even be even worse than that. So can you get the efficiency you need when it gets cold, right? And then how much heating cooling do you have and how much energy does it cost? So there's always that cost balance. We're changing, we're getting a very efficient system according to the market research, or excuse me, the manufacturer's specifications, but how much does it cost, right? Okay, so here's some just high level pros and cons. I just tried to throw some out there. There's much more to it than this. So the pros, we're going to go down the pro side first. Heat recovery and I'm going to show you what that looks like, is setting up the system in a way where if I'm really cold in my apartment, I can run heating, but if my neighbors or somebody on the same floor is on the south side and they need cooling, they can run cooling at the same time, okay? So you need a heat recovery system to be able to achieve that. If you don't have that ability, you're basically what they call heat pump mode, where you're either in heating or you're either in cooling if you're all at that same condenser. You can have fewer pieces of outdoor equipment with these systems because, like I said, one condenser can handle multiple terminal units on a floor. So you go to 15, 20 units depending on the manufacturer. It's an all electric solution. We're all striving for all electric. There's a cold climate solution. There's multiple manufacturers that provide cold climate solutions for VRF, for heat pumps. And then they really do have high efficiency ratings if you look at the testing reports. Now, if we go to the con side, when you go to that heat recovery mode where somebody can do heating and somebody can do cooling at the same time, you actually have an extra refrigerant loop in the building, which means you have more refrigerant in the building. You actually have higher costs for materials and installation. The smallest units we can still get are somewhere around 4,500 BTUs. On the heating side, that's still too big. We could use something that's somewhere between 1,000 and 2,000 BTUs on heating. But then again, for cooling, we need, probably at least double or triple that. If you're trying to bill your tenants for heating or cooling or both, you actually have to have a third-party person process that information so that you can parse it out by apartment, because you've got one condenser handling 10, 15, 20 apartments, right? So you need somebody to handle that billing for you. And then if you do not have heat recovery, overheating is a common result of a heat pump system. And I'm going to get into that a little bit more. So again, this is heat recovery system. We have 3 refrigerant loops running through the building. That extra loop is so that you can share the refrigerant and exchange heat from one apartment to the other. That's what makes it work, the simultaneous heating and cooling. That's what makes it more comfortable. Is it market rate or affordable? If it's market rate, you're probably going to put more money into the building. If it's affordable, you got to be more careful of your budget. Are you obligated to provide cooling, yes or no? If you are obligated, then you probably want to go with a heat recovery system. If you are not obligated, a heat pump system might be right for you. And you can just say to people, if it's warm in here, open your windows, right? That's not in your contract. Who's paying for cooling? Is it the owner? Is it the occupant? That also is a question of whether or not you should put this in. And then the cost differential, I've heard quotes from 15% extra for heat recovery to 40%. I think it's closer to the 15% end that I heard. 40% was more years ago than the 15%. So I think people are starting to get used to it a little bit. So design considerations, sizing is really important. I'm sorry, I'm trying to get rid of the pictures over here on the side so I can see this, my screen. Page back up. So it's not possible for small passive house spaces with respect to heat load. You can't properly size this wall mounted head is going to come at a minimum of 4,500 to 6,000 BTUs. The load in a multifamily apartment is probably 500, right? So you're like 10 times oversized. And then you want to change the settings so that the fan shuts off when it's not calling for heat. They come from the factory as a fan continuous mode. So even if it's not calling for heat, the fan's going to run on low. You definitely want to make sure that the settings in the unit are set so that your fan is not calling for heat when the heat is not needed. Stratification of temperatures. If you're using a wall-mounted unit with a VRF system that's up high, you're going to have stratification, right? The temperatures are warmer at the ceiling than at the floor. So higher return temperatures lead to lower efficiencies. Also, if you're in a heating dominant setting, say you have a historic building that's more heating dominated, or you have a single family home that's more heating dominated and you're using a wall mounted unit in a mini split system, you want to maybe go lower, use a floor mounted system that it'll increase the efficiency. Most of our large scale projects, our dense projects in North America will be cooling dominated. So these high wall mounted ones are okay, but you have to consider in an apartment, a 1, 2, 3 bedroom apartment, you're going to need one of these in each area that has an exterior wall. So you're going to be drastically oversized. Okay, so if you can, you don't want to do a unit in every room. Zoning. If you're going into heat mode without heat recovery and you're either going to be in heating or cooling and not the option to do both, you want to make sure you zone these floors properly. So you can see this is, if you look at this, we are facing this wall here is facing southwest, this is facing southeast, south is this way. So you want to make sure you zone your apartments together. You also want to make sure you put spaces with the same heat loads and temperature profiles on the same zone. This is a case where this is a historic retrofit. The stairwells and hallways could not be insulated according to historic retrofit, but the bedrooms are super insulated. So these, if we had them all at the same temperature setting, would be calling for much more heat than the bedrooms, or excuse me, than the apartments. So they're driving the refrigerant flow in the lines. And as long as you have refrigerant flow, you have this heat bleed that's going into all of the spaces on the same zone, because it's like a refrigerant loop. You can't have anybody just completely cut off. The condenser wouldn't run properly. So even if this stairwell was set at 70, like the apartment, it would run more often. And if this apartment didn't need heat, it would still get heat. And so you're going to wind up with overheating. These are infrared images of the units at the house at Cornell Tech, right? So this is a heat pump only system. This is one apartment that had a wall mounted unit and a floor. Most of them had floor mounted units. Neither of these rooms are calling for heat right now. And yet you can see the refrigerant charge in the line is making the unit put out about 90 to 93 degree temperature. So obviously the building is warmer than 68 degrees set point, right? All of that heat is just loading up into the spaces. And then finally, you really want to make sure you're protected against snow and ice. You don't want these condensing units. This is just a little mini split system showing, but it can show the impact of snow and ice on these units. So you have to make sure you're prepared. So design consideration summary: if cooling is desired or being provided, seriously consider heat recovery. Limit the number of terminal units in each apartment, not necessarily per space, but in each apartment. Consider population in the space. Is it affordable multifamily where you're going to have really high density and a lot of internal gains? Is it market rate where you're going to have less internal gains? Are you going to have seniors that really want a warm apartment, right? Like all of these things come into play. And then zone for orientation, space loads, and set points. Make sure that all three of those things come into play when you're doing this. Operations consideration. So as I said before, most of our multifamily buildings will be cooling dominated. They usually have set times when they don't have heat recovery that they change over from cooling to heating, and then in the spring from heating to cooling. It depends on what you're obligated to do for cooling, but you may want to extend that cooling window. So if you normally turn over from heating to cooling October 1st, you may want to consider November 15th. These three thermostats are from 3 different VRF projects in heat pump mode, and they are showing you that the set point on the thermostat is way lower than what this one's off. And this, you know, they're way lower. And this one here was 30 degrees outside. This one was 40 degrees outside. And I think this one was about 50 degrees outside. That was just recently. So these people wanted a cool apartment, but they can't get a cool apartment, even with their windows open. So really keep that in mind when you're doing this. Dealing with passive house windows in multifamily buildings have limited opening profiles. So even if you say, well, it's very valid to open your window, you know, and cool off your home, it is. But if you only have a 2-inch or 4-inch opening and an awning, you're not getting a lot of cooling from that outdoor air, no matter how cold it is outside. So you have to keep that in consideration. Dealing with airtight envelopes, we just don't lose heat to the outdoor elements as we do. So the internal gains dominate. Commissioning, please keep this in mind. Commissioning is an ongoing task for the first year or two. It is for all buildings really, but our passive house buildings are being so strictly reviewed that, and we're expecting them to work better than they are. Just keep it in the back of your mind. Commissioning takes a year or two. Our engineers are good, are really the ones, and we're using repeat engineers. Each building is different, and each building's occupants are different. And then we're missing the point where we're educating. We're turning over the building and we're not getting to the O&M staff and the residents. And that's a really critical link. We have to get to the people who are going to take over the building. I was talking to the building manager of this building, and he had no clue that he should expect an overheating problem. And I said, I understand. That is a big failing of where we are right now. And our team is really trying to rectify that. So some of the things we don't know still are the actual operating efficiency or COP of these systems. I don't know, I've heard that the manufacturers have these great monitoring systems and, you know, can do all this analysis. I haven't seen one in any of our projects. And we need to try and figure out what it is for each manufacturer, what it is they own, what it is we need to see, and make sure in design that we're going to get that, because we don't have enough data points in the system to be able to evaluate. They supposedly can get it for us, but we just can't get it because it hasn't been ordered up front. How do we get owners to install this monitoring system for better analysis? How do we convince them that it's for their own good, for the good of the occupants' comfort, for their monetary budgets, you know, like how do we get them to see this? What's the simplest and best monitoring systems? Like, I don't know that either. And then what's the optimum level of refrigerant line insulation? And I ask you that because in our recent passive house project that I've been evaluating the temperatures on in a very painstaking manual way, the hallways and common areas are all overheating, and the hallways in particular, and I think that's because the refrigerant lines run down them and the domestic hot water recirc lines run down them. I don't know which is the blame, but they're like 8, 9, 10 degrees over their set points, and the apartments are not. So it has something to do with the line sets that are running down the center. So moving forward, this is what I mean. We always want to continue collaboration with the VRF manufacturers to find solutions for comfort and efficiency. We need to increase our education of our operation maintenance staff and our tenants so that they know how to react in their apartments and what to expect. We are working on real-time education at the touch of a button. So like, here's your building, you have an app, you click on cooling, you click on ERVs, and it tells you exactly what it is in your building that you have and how to maintain it and what to troubleshoot. So we're really working on that. Keep pushing everybody for monitoring simple, you know, but comprehensive, simple yet something that tells us something. And then continued outreach to you guys, because I'm sure some of you have some great ideas for me right now. And then honestly, not to bag VRF manufacturers, but continued review of alternate solutions. FIA's had this great presentation the other day on heat pumps that are coming, you know, individual solutions and things like that, and retrofit solutions. We got an overview of that today from one of my staff, and it looks fantastic what's out there in research and development. So the PTHP is a packaged terminal heat pump unit that's cold climate. And then low temperature hydronic, which can be hooked up to heat pumps as well, is a very viable option for heating and cooling. The last thing I want to say is that for future considerations, we really should be considering, even though we have a champion for climate change in the White House right now, we know we're headed down this road of heat waves and hotter temperatures. So we got to keep that in account. Winter performance, we still must be able to meet the cold snap days, but handle part load efficiency. And then efficient low carbon technologies must perform in all climates and weather conditions. So that's the thing we're looking for. So that is my spiel to you guys. That's the end of my presentation. I'm going to stop sharing my screen. And I welcome comments, suggestions, solutions, but that's what works for me. And I want to say, I just want to reiterate, please don't throw out VRF. It really just takes some patience and some troubleshooting. The last one we just did, 200 Tyler, which is a historic retrofit, does not have as good windows in it because it's historic as a normal passive house project. And it just had some funky temperature set points in, say, like a stairwell that wasn't insulated versus the apartment. Once we got those under control, everything calmed down in the building. All the apartments are like within 1-2 degree of their set points, except for maybe 3 or 4. And I need to look further into why those are outside their set points. But we had a little bit of an uproar when people moved in about being uncomfortable, but it's completely settled down now. Thank you.
Sorry, Lois, do you have a drink of water here? I'm just gonna, I put the list of questions, and Perry, I did see you, and I'm adding you to the queue. So there is a long list, and there's some good questions here. So for those that Lois, hopefully you don't mind sticking around, because we're probably going to the after hour with this. So hang in there, everybody. All right, Kevin from Calgary. Question, is there a Chinook happening today in Calgary? We always like to check in on the Chinooks.
That's not a question for me.
No, it's for Kevin, but he's coming.
Yeah. Oh, yeah, there is. That's the one thing about Calgary's climate, is that it seems like there's relentless, unceasing Chinooks. So anybody that in the Alberta legislature specifically that thinks that climate change just might not be happening, it was +9 degrees and raining in Edmonton yesterday, in the middle of January. So that's crazy. But yeah, we've had almost continual Chinooks. It's quite wonderful. Now, I can't remember what my question was, but I think it had to do with cold climate. And I think, Lois, you managed to answer most of that. But are very many of your projects cold climate, and what are the issues you found there?
They are cold climates. And so what happens is you get a reduced capacity on the condenser in the wintertime, but because our heating is such a small fraction of our cooling, we're sized appropriately for heating. We don't ever run into trouble in our large scale projects with heating. There's never a cold enough day that, and also the temperatures don't change inside these apartments very quickly, right? Like it takes days for these, even the historic one I was just telling you about. There's several tenants in there that have their thermostat set at 62, have since they moved in, and have their windows open, and the department has not fallen below 68 degrees. So, and part of that is because of the refrigerant line, and part of that's because of their internal gains, but we don't have any capacity problems with cold climate with the VRF systems at all. Okay. We haven't seen any.
That's interesting. It's a similar experience. Like my experience is mostly single family. Interesting. But the thing about that is I always have to tell my clients, look, it's not a rapid response system.
Exactly.
You know, it's going to take a full day for temperature to change if you want it a little bit warmer, and dependent on what's going on in the sun. So, you mentioned the exposure. So is there a huge difference between south and north facing? I would say, yeah, but what's your feedback on that?
It really, you know, I was looking at it today because today was the first warm day or sunny day that I could get into the system. I have only been in the system for about a week, and it was cloudy for several days. And so we had heard that there was some drastic overheating on the south, but I think that was because we didn't properly set the set points in the colder spaces to lower temperatures, and they were constantly calling for heat and putting refrigerant into the building. So since I looked at it today all through the sunny portion of the afternoon, and there was, like I said, maybe 2-3 degree difference. And I don't even think there was much of a difference from the north to the south side. I looked at the whole building several times today. So it looks like it's doing really well. We were a little bit panicked at first, you know, because of the complaints that were coming in, and they're elderly and they're there all day long, right? So they're letting us know if something's not good. But no, I'm not seeing much of a drastic difference, but I am going to be watching it for the next several days because we're supposed to have more sun. So I'm going to see if there's a escalating temperature issue.
Kevin, is that it for your questions? Excellent. Okay. Julie from Cambridge had a couple of questions and lots of great comments. So thanks, Julie. Your turn.
Sure. Hi, Lois. How are you?
Hey, Julie.
Yeah, thanks for a good presentation. Amen on the commissioning, monitoring, and patience. We've got VRF in most of the buildings we do. Some have better enclosures than others, and we've had issues with, you know, on a -14 day in Cambridge, maybe it doesn't quite get to 74 or 80 that some residents would like.
Right.
We've had, you know, we've got residents that have figured out if they hang a ice pack in a Ziploc bag over the thermostat, they can get it a lot hotter in their unit, which I'll share that photo with you at some point. My question is, we're looking at, because of the damage refrigerant does, is a hex system. So it's basically the VRF's on the roof, you know, it brings refrigerant to, I'm going to call it a mixing box, but it basically at that point it converts the heating or cooling the water that runs to a like a Wayland unit type stuff. Are you seeing any of those? That's my main question.
We haven't done them yet. We've been recommending them to project teams who are hesitant about refrigerant in the building. We haven't done one yet. The most of our systems are just straight VRF, but we're definitely on board with seeing something go in. You know, I think we might see one going in a retrofit in a dorm in New York.
Thank you.
But good systems. Good. I think.
Yeah, I'm looking forward to it. Yeah, we have it designed, but you know, it's not going to go in for another year. So I just wondered if you had any lessons learned on that.
Not in the field yet, no.
And I didn't see vertical fan coils in your distribution in units. Is that something you don't do, like a ducted vertical fan coil?
Actually in the one that I was showing you with the zoning, they actually have closets with a ducted vertical, but they're only one bedroom unit, so it's like a very
small. So it's a short duct. Yep. Okay. Thank you.
Julie, you had a couple of questions. Is that all you need today? Perfect. Okay, moving along. Tom Phillips, you're up.
Well, thanks for the great presentation and good to see you. I've been looking into variable capacity heat pumps to be able to handle from, you know, real small cooling loads to big loads, not only over the year, but over decades as the climate changes. And how do VRF systems have that ability, or is there a further tweaking you need to do to handle future increases in cooling loads? I guess the related question is, how are you designing for peak cooling loads in terms of weather files and so on?
You know, we don't use the Passive House software for designing to cooling loads in multifamily. I have verified the software's algorithms for heating in single family and like duplex, smaller scale building, and it's perfect. Like the load calculation is perfect, but I have not had the opportunity to verify the cooling. The engineers generally use their load calculation tools. We check the calculations. They're not using future climate files yet. I know other consultants are using future climate files to verify this. I think we have really think we have plenty of capacity built into the systems to handle quite a bit of change over the next 20, 30 years before the end of life of the, of the equipment. I think that I feel pretty confident that the cooling will be well handled. I'm sorry, that's not a great answer, but we are not currently using future climate files.
Do you use like design summary years or some other peak load?
We use the ASHRAE design, the 1% or the 0.6%, that design temp. And I see that's why I think it's okay, because they're using an hourly design calc, and we know these systems aren't responsive hourly. So I think there's a lot of buffer built in based on the fact that the past hours, if you look at the profile of the peak, it's even shifted from where a normal peak in a normal building would be. It's like at 2 hours ahead. Excuse me. Like if my normal peak for my building, my room or my apartment is at 4, my passive house peak is at 6. So I think we have plenty of capacity built in just because of the lag in response in a passive house project.
Yeah, until you get real hot, humid nights or something.
until you're in Vegas.
Yeah. All right, thanks.
You're welcome.
All right, thanks, Tom. And if you're reading the chat, Peter gave us the update. So Kevin will be wearing his parka in about 4 hours. So Kevin, get ready. Enjoy your t-shirt now. It's coming. And you too, Leah and Celia. Damien, we're going to Thursday. How's Thursday, Damien?
Thursday's sunny. The point you were making about the heat exchange not being renewable, I didn't follow what the point was that you were trying to make about air source heat exchange and ground source heat exchange.
So I have seen, and in federal documents online and in incentive programs, I have seen geothermal heat pumps considered renewable energy sources. And they are not renewable energy sources. And like in federal documents, and I'm like, no, this is wrong. So I just wanted to make sure everybody's on the same page. You still need electricity to run these systems to produce the heating and cooling that you need. It's not solar, it's not wind, it's not hydro. You are using some sort of fossil fuel to run this heat pump.
Okay, and the second thing I suppose was I'm curious whether AI isn't going to be better at setting our atmospheric conditions within buildings than humans are. Research out of one of the universities here said that if you have a fan and set your thermostat for 26 degrees, then you are actually as comfortable as you are if you set your thermostat for 22 degrees. I'm speaking Celsius, so so the movement of air changes our subjective perception of temperature, and certainly in those examples you were talking about of the split between high and low heating, where our head's at makes our different to what our perception of temperature is, irrespective of what the reality is.
Right.
So, other than just people getting used to the buildings and buildings that actually work like they should, it's also this fact that, humans probably aren't all that good at setting thermostats.
Well, it's scientifically, it's statistically proven that you have women and men in the same space and you're never going to come to an agreement, right? Like never. So like we've had wars in our office over thermostat at some point. So,
exactly right.
Yeah.
Exactly right. Now, I remember one of the most amazing stories I ever read about thermal solutions was, in Cradle to Cradle, where he was talking about keeping a shop floor heated by pumping cold air in from on top. So
Oh.
he made a thick thermal blanket over the warm air that he was putting at the level of the workbenches, so that it only went up to about 6 feet high. Most of the shed was actually filled with cold air, and only the human zone was actually filled with warm air. And I thought,
That's nice.
That's the sort of thinking that we need.
Absolutely. That's like the radiant heating aspect of things, right? Radiant cooling. Like if you can keep that radiation just around you, everything else can be colder.
Yeah.
Yeah.
Thanks. Great presentation.
Thank you.
Excellent. Thanks, Damien. Next up is Michael from Bethlehem, Pennsylvania.
Hey, you keep talking about there being like temperature bleed through in the zones that are off. Is there a technical name for that I'd be able to find in like an operating manual?
No, I don't think so. Because when we did the house at Cornell, you know, the first tower that we had in the US, Mitsubishi had to actually recreate it in their laboratory to see how much heat was actually coming out of it. And it was like 500 BTUs when the system was not calling for heat. And that was the design load. So we were just like, oh, Jesus Christ. So it's a minimal amount of refrigerant that has to get back to the condenser, right? There has to be this circular loop. If somebody's calling, there has to be a circulation of refrigerant. And so the minimum amount that was calling, the fact that they were floor mounted was even worse, because then they became like convectors. So the warm, you know, the air was rising over them and then convecting into the space. So I don't think there's anything in the manuals yet. The manufacturers are aware of it now. Everyone's very aware of it now. It happens at any unit you're using, but yeah, it's just the fact that refrigerant has to keep running through that unit if you don't have the heat recovery mode.
Okay, thank you.
You're welcome.
And Stuart just put a good point about VRF. So read the chat from Stuart. Good to see Stuart. Harvey's got like 3 or 4 questions. Let's see which one he asks. And guess what? He's not going to ask about cost today. At least not right now.
Because Lloyd's here. If Lloyd wasn't here, then I could ask that question.
Yep.
So Lois, thank Lloyd. Otherwise, I was going to put you on the spot with that question. I have actually 5, but a lot of them have been answered. But the last 2 that I came up with, and I apologize in advance. This is an area I don't know a lot about. So I'm just going to ask a couple of simple questions, and hopefully I don't make a fool of myself. Internal heat gains, I wrote down, what was learned from projects, or all projects different? You had said they're all different, but is there anything that's being generalized from that? That's question 1. And then number 2, again, like I don't know a lot about it. You said heat in hallways and stairs. I was just wondering, can the hot air be used for efficiency? And was this a surprise to you?
Okay, so the first one, internal gains, we've known from the beginning of modeling, because we were looking at, because the cooling was so high, we were like, whoa, what's going on, you know, from the first ones. And what we saw was that just people and the normal appliances was at least 2 to 3 times what the solar gain was if we had a rational solar gain coefficient of, say, 30%, right? And because on high rises, you're not really doing, in the US anyway, you're not doing exterior shading very much. It's very costly, birds sit on it, you know, stuff like that. You might do vertical depending on the designer, but you don't do horizontal vertical shading. So, but anyway, we saw that the solar gain, the reduction in cooling to solar gain was much less than the reduction than what was happening internally. So, and that's proven to be true, because as I showed you those thermostats, right? 30 degrees outside and a room is holding at 73 degrees. That's 3 family members in the house, maybe a computer running, a TV running. And so that's what we were seeing. Okay, I'm sorry. The second one was, remind me again.
Sorry, the second one was just that you had said something about heat in hallways and stairs.
In hallways.
Yeah, and I was just wondering if that hot air can be used for efficiency, and was this a surprise?
So this was a surprise on this particular project because this is a historic project, and the windows in the units are very large, and they're not passive house level windows. So normally what we see in our passive house projects is that the heat's kind of the same throughout the building. In this building, we see that the heat in the hallways is much higher than the heat in the apartments. And so I'm thinking that we get a little bit more loss through these windows than we are on a normal passive house building. but between the refrigerant lines, which are run down the hallway, and the hot water pipes. So my team kind of has to do a calculation to see which is the culprit in what's driving that, but I think probably both are. And I think we need to look at what the real efficiency level of the insulation on these central systems should be. We're doing code. We always thought code was fine. In our normal passive house projects, it didn't seem to reduce the energy use enough to offset the cost of it. But in something like what we're in now, or we might do what you're suggesting, Harvey, is maybe we can recirculate some of that heat from the hallways and reuse it in the stairwells. The stairwells in that building we had set to 62, the hallways we had set to 65. Most of the hallways were running 73 to 74, but the stairwells are still running at 62. They're setting at their set point. So maybe we could just blow some of that into the stairwells and kind of balance out the building a little. I think that would be a good option.
Was there any bleed through into the other unit? I think Michael asked it, but was there bleed through from that into the other units, and that's into the occupants' units? Is that what was causing some of the problems? So is that a door issue? Because were the hallways were the units insulated through the hallways?
I don't think there's much heat gain from the hallways. I just think the temperatures are too similar. Most of the rooms are running at around 70 degrees and the hallways are 73, 74. So that heat transfer is not that large. I don't think that's driving the apartments, but I do think we could use it. I do agree with you. I think that possibly an air collection strategy or better insulation in the hallways really could have done the job.
Or the better windows in those.
Or, yeah, but you know, historic, they're strong.
Well, that's where Michael comes in. He can tell you all about it. Okay, thank you, Lois.
Yeah, I know.
Presentation. Thanks for taking my questions. Appreciate it.
Thank you.
Okay, Zach, over to you.
All right, thank you. This is fantastic. So none of the work that we do at the Accelerator would be possible without the support of our sponsors. So I want to take a moment to give these fine organizations a big shout out and encourage you all to work with them in your projects. So our founding sponsors are 475 High Performance Building Supply, Baxt Ingwe Architects, Glavel Foam Glass Gravel, Minotaur, Mitsubishi Electric HVAC US, Partel, RDH Building Science, Stocorp, and Zola Windows. Our stakeholder partner is NYSERDA, and our patron sponsors are BR+A, Brennan Insulation and Air Tightness, Initech Windows and Doors, and US Engineered Wood, T-Stud. We've got some really exciting stuff going on next week. The first one is a panel that we are doing with AIA New York, their CRAN, which is the Custom Residential Architects Network. We're working with Dennis Wedlick on this really cool panel, which is a virtual film festival of video shorts from 4 different project teams about passive house projects and practice, followed by a panel discussion that I have the distinct honor of moderating. So I'll share a link to the registration page for that. It's all that is done through AIA New York, but we're really excited to be able to share about passive house practice, both construction and design, with the AIA New York community next week, and hope that you'll get some friends to attend, because it'll be a good primer. It unfortunately conflicts with another wonderful presentation and event, the Construction Tech Tuesday. So you'll have to make a tough decision about which one you'll attend. This will be a really fantastic presentation from Aaron McCormick of 475 and Kevin Brennan, the co-host of the Construction Tech Tuesdays. They'll be talking about fluid applied air barriers. And then our Wednesday happy hour will feature Deborah Moelis, a frequent collaborator with Lois Arena. Deborah is with Handle Architects, and she's designed many of the most significant passive house buildings in North America. She's going to be talking about the University of Toronto Scarborough project that we actually have heard about before from Maureen Sanchez of RDH Building Science. Deborah will be focusing more on the design, and then importantly, talking about how she guided helped guide the university to commit to passive house on this important project. So please join us next week the happy hour. Thank you.
Awesome.
Well, thank you so much, Lois, for sharing your knowledge and experience with us. We definitely appreciate it. And we have more questions, as always. So appreciate you sticking around. And for all of you who have to leave, I hope you have a great night. And we'll see you, as Sean would say, in, is it 6 sleeps or 7 sleeps?
Well, it depends what's going on these days. You know, you could see you in 2 sleeps. You could see us in 5 sleeps or 6 sleeps. There's so much going on, but we'll see you soon.
Yes, we will.